Yeah, welcome back to the FDP, that is Faculty Development Program. Now we have our second speaker. It's my great privilege to introduce our highly distinguished guest for today, Dr. Debashish, sir, a renowned research expert and influential figure in the world of academia and the technology. Dr. Debashish brings a wealth of experience, expertise, making him an inspiring personality in both research and education. Dr. Debashish is currently a research expert at NRDIO and an associate editor at IET and a proud member of ACM. His contribution extends further as an associate editor with the uh, micro technologies, then demonstrating his broad and deep understanding of cutting-edge advancement in computing. In addition to his current roles, Dr. Debashish also serves as the professor at West Bengal University of Technology, where his academic leadership has significantly influenced the next generation of tech professionals. He also holds the esteemed position of chairman of Computer Society of India, contributing to the advancement of computing community nationwide. His academic credentials are equally impressive. Dr. Devashish completed his PhD in computing specialization in computer system networks and telecommunication from the prestigious Jadavpur University. He also holds a master's degree from the University of Calcutta, further solidifying his expertise and academic foundation. With his vast experience in research, teaching, and leadership, Dr. Debashish continues to shape the future of technology and innovation. Today, we are fortunate to have him deliver a session on quantum machine learning, a transformative field at the intersection of quantum computing and artificial intelligence. Without further ado, please join me in welcome Dr. Debashish, sir. Over to you, sir.
Thank you, Vagish, for your kind introduction. And thank you for giving me the opportunity to discuss, rather share my thoughts in the domain of quantum computing and quantum machine learning. I must thank to the organizer, Priyadarshini Madam, for your invitation. And also, I hope that we'll be discussing some of the very interesting topic of quantum computing, and obviously in the domain of machine learning, how this quantum computing and machine learning coming together, we'll be discussing. And second part, we have my colleague, Dr. Mohan Nandipal. She will be discussing on the hands-on training, practical hands-on training on IBM Q, Amazon Bracket, and with our existing projects with METI and Amazon AWS, we'll be discussing that part of quantum computing. And you know that I like to mention that I started this journey of quantum computing in the year of 1998. Okay, so that time everyone is talking about quantum computer will come within 5 years, 10 years. But the major challenge till date, till 2024, we are facing that this quantum computer cannot be accessed at room temperature. So what was the problem there that time when I was working in the quantum lab of Edinburgh, where we have observed that the quantum devices, the electronics part of the quantum device, they work only at very low temperature. Okay, that is minus 273 degrees centigrade, and also at very low pressure. Low pressure means 10 to the power minus 12 millibar. 10 to the power minus 12 millibar. It takes 15 days to vacuum a chamber. You know that it was very boring, or at the same time very interesting also. Interesting in the sense that you have to process, that vacuum the chamber with rotary pumps, stator pumps, various kinds of pumping systems are there, which will help you to vacate the whole system, means evacuate the whole system of the metallic chamber of the quantum computer. And the pump slowly vacate the chamber, and it gets to the lower pressure, 10 to the minus 3, 10 to the, after say 7 days, 10 to the minus 6, maybe after 10 days. And after maybe 12 or 15 days, we can reach around 10 to the minus 12 millibar. So lots of pumps are used to vacuum the chamber. And also we have to keep the system, means the quantum computer, which is in a enclosed chamber, at very, very low temperature, means cryogenic temperature, minus 273 degrees centigrade. So I worked in the domain of superconducting quantum devices. quantum dots, quantum well, and quantum wire. These are the very basic components of a quantum computer. Okay, quantum well is like a well where electrons can move in a one direction. Quantum wire, the electron can move in single 1D, and quantum dot is a very small dot where electrons are confined in 3 dimension, so electrons cannot move. So these are the three basic circuits or other components that we have developed in the year 2005 in Scotland. The scientists are trying till that, last 30 years, that how to make these devices at room temperature. Unfortunately, till date, none of the scientists, successfully they prepared the quantum computer at room temperature. So that is the reason. Still, we are working into cryogenic temperature. I'll show you the pictures, and the enclosure at very low temperature, low pressure, we are keeping it, and we are accessing that quantum computer through our existing laptop. For example, I am in this FTP. We are connecting with 13 participants, I can see, and where we are using our own digital computer. Now, same computer we can access to the login. I think Moha madam in the second half will show you how to log in to the quantum computer, live quantum computer. She will demonstrate you live quantum computer, and using my classical computer, I can connect to the quantum computer, which is kept at very low temperature, low pressure, somewhere in the world, right? And through that, actually, we are accessing the devices, circuits, logic gates, and the memory, and all this, everything. That these are the very basic components. So full quantum computer is still yet not available. So it is a combination of classical to quantum. So we are connecting these things together, right? So let me share the slide first. Then so today's topic is quantum machine learning. The quantum means it comes from the quantum physics, and machine learning is now so popular. Everyone is talking about machine learning, and also we have a BTech in computer science, machine learning, AI/ML. So machine learning is a buzzword, and industry is running on it. So quantum machine learning is a amalgamation of quantum computing and machine learning together. Okay. So I am discussing about this circuit, right? I was discussing about the chamber. This chamber, actually, these are the electronic circuits, and these are metallic cover. Can you see this metallic cover? And this metallic cover goes down, and the circuits, we have to make the chamber vacuum. When the metal goes down and connected to this, these dots, that, then what will happen? It will make a enclosed chamber, and we have to take it at very low temperature, minus 273 degrees centigrade. This full vacuum. So the circuit inside, this is the circuit actually. The circuit inside goes to cryogenic temperature, minus 273 degrees centigrade. Minus, mind it, minus 273 degrees centigrade. And also, we are using various pumps to make it in low pressure, 10 to the minus 12 millibar order. So I worked personally in this kind of quantum computers in 2005. And also in Australia, I worked in 2009, 8, 9 that time. And in India also, we have quantum computer. This is a quantum computer. I think maybe you have seen it. This is in Calcutta, right? And I think 1 month before we have visited this center. So this is a quantum computer. But unfortunately, it's a very small. This only 1 qubit is available. Now they are upgrading to 2 qubit. So if you upgrade it, the cost of the device will go high. Similar to our computer RAM, if you upgrade it from 32 GB to 64 or 128 GB, your circuit cost goes a little bit higher, right? So by this way, actually, this quantum computer works. And this is the enclosed chamber, as I told you. The chamber goes down during the operation. during the logical operation. Okay, this is the first quantum computer in Calcutta. It was developed in last year, right? Now you see the quantum computer started by the companies like Google, IBM, Microsoft. Okay, and Google also has their own platform. Amazon is also coming to the picture. Okay, so everyone nowadays in this world want quantum supremacy. Means they want to have a that 100 qubit or 1000 qubit. Even it was reported that IBM developed 1000 qubit quantum computer. Country like China, they are working on this quantum computer. They are doing communication from their country, from China to moon, and also the other part of the galaxy using this quantum computer with very high speed communication called quantum communication, right? So these are the very interesting areas, and everyone want to achieve this quantum supremacy. Even government of India started NQM, National Quantum Mission. They are interested to explore this quantum supremacy in the field of quantum computer. Now, what is the problem? What is the problem of classical computer, and why we are thinking of quantum computing? Okay. This is the biggest problem, rather. So, quantum computer actually we use sequential data processing, one by one, but quantum computing can process it parallelly, 1, 2, 3, 4, 5, 6. Everything can be done in a parallel processing system. We need a parallel computing system. That is the reason this sequential data processing is slower, right? Also, the problems such as cryptography, optimization, that complexity is very high. I think the FDP topic is also, I've seen quantum computing also in security or cryptography. So, in order to achieve the high quantum cryptographic circuit, the complexity is high. So if you use the quantum computer, it can be resolved very simply. So that is the reason quantum computing is essential to develop this cryptographic system. So after this quantum computer came to the market, we are calling it now post-quantum cryptography. Post-quantum means after quantum, right? So we are calling it post-quantum cryptography, right? So it is very difficult to simulate the quantum system. So see, when you're coming to this quantum computer, so we have two important things called parallelism, means parallel you can do it, and superposition, right? That can explore with many solutions with exponential speed up, experiment to the n order. We can go for the speed. Speed is very high, extremely high compared to the existing quantum computer. And also, there is a feature called entanglement. This is the most important part of quantum physics, entanglement. I'm not going to the physics part, but these are the three properties like superposition, parallelism, and entanglement. Okay, so these are the actually basic principle. Using this, we are actually developing this high-speed quantum computer, where normal system have n qubit. You know that if a n qubit quantum computer means, say 4 qubit quantum computer means 2 to the power 4 states are available. 100 qubit means 2 to the power 100. So you can understand the speed of the quantum computer goes so much high, right? Instead of normal classical computer 0 and 1, we are using qubit, quantum bit called qubit. 0, 1, and also their entanglement exists together, right? So it forms a potential platform for multiple calculations at once. Can do multiple calculations at once, right? So there is a parallelism. So I also worked in this facility at Melbourne. We have a collaborator, Rajkumar Bhuya. I worked in this university, University of Melbourne, where we have this IBM-sponsored quantum computer. And it is so several thousands of dollars they have invested for this quantum computers, right? IBM. Now the term quantum, it might be triggering some from very basic idea from atoms to molecules. That molecule level computing is possible. So quantum computers are made up with similar ideas. So computing using the atoms, so we call it different types of bits called qubit. And qubits acts as a both particle and wave. Particle and wave, that Einstein relationship we can understand. Now there are four different types of quantum computer. I personally worked, I told you, in Edinburgh, Scotland, in this superconducting computer, qubit. Superconducting means, again I am repeating, that minus 273 degrees centigrade. If you make it so low temperature and low pressure, that is the minus 12 millibar, then it becomes superconductor. Superconductor means, that resistance is almost zero, right? So I square R means power, no power loss, reversible. If R equals to zero, because of superconducting I square R, power requirement is almost zero. So we are talking about reversible logic circuit, right? I've seen in this FDP, I think Professor ISG Indonesian Gupta, he is also giving talk on reversible computing, and reversible computing starts in this domain of superconducting qubit, right? Where R is equals to zero. So power P equals to I square R, that is also almost zero, right? And this quantum computers are all reversible in nature. Means number of input and number of output is same, and also power requirement is zero, almost zero, right? Very low power requirement, and that is the reason that this quantum computer requires very low power circuits. Also, other than this superconducting qubit, we have topological qubits, photonic qubit, and also trapped qubit. Okay. One company called IonQ, they're in USA. They are also using this trapped ion. That is quantum dot kind of thing. Photonic means light, photonic crystal, optical, right? Optical quantum communication. So let me explain it here. So superconducting qubit is relatively high coherence time and suitable for error correction. You know that quantum, lots of error is always error is the biggest challenge in the present circuits. For your information, quantum circuit is not yet stable because of lots of noise. Noise is the biggest enemy of quantum computing in terms of measurement, in terms of the design of the logic circuits and measurement. So IBM's IBM-Q and Google's this platform, SimCare platform is used for the superconducting qubit operation. Okay. Photonic means, you understand, photonic is light, right? Photon. So using the photons also, at a small level of photons, we can have the quantum computing facilities called photonic crystal. We call it photonic qubit, where we can see that speed and resistance of environment is interference is comparatively less, and these companies like PSI Quantum and XNDU, they are also using this this platform. There are various companies, like I show you IBM, Google. 90% companies are using superconducting qubit, and few companies they have started. Few means only few, 5% to 7%. They are using either photonic qubit or topological qubit. These are the various topological circuits. Microsoft's, they start high error resistant circuits using this topological qubit. But the complexity of the circuit is a little bit higher in case of topological qubit. Otherwise, if it in terms of simplicity, this superconducting is very simple. But optical, the speed is very high. The complexity is a little bit higher in case of topological as well as trapped ion. Trapped ion means electrons are trapped, and as well as that ion can be transferred. One by one atom can be we can transfer from one place to other place. So the entanglement and all the physics can be resolved using this trapped ion. So IonQ and Honeywell, these are two US based companies. They are especially IonQ is one of the market leader for trapped ion technology. So these are the various kinds of quantum computing structures, rather logic circuits, means basic electronics of quantum computer. Now, as I said, that in case of classical computer, we have only 0 and 1. So if you see the quantum computer, it is that 0 and 1 exist together, can exist together. So it forms a sphere. 0 is there, 1 is here. So you can say 0 is ground state, and excited state means 1. So the entanglement state, intermediate state may be here, anywhere in the sphere, anywhere. Just like a football, where the point, any point, intermediate state can be anywhere on the circle, right? Sphere. like a football, right? Like our Mother Earth, right? So the quantum states where we are talking about alpha is the probability of 0 and beta is the probability of 1, where alpha square plus beta square equals to 1, right? So the state of qubit, state means what? Which state at present it exists. It depends on the probability, alpha and beta. So alpha is the probability of 0, beta is the probability of 1. So these are the various values of alpha, beta in terms of cos theta, sin theta. I'm not going in details of it, but this is called block sphere, right? Where the circuit states can be explained. Where the that like a football, just like our we are in Calcutta, right? Maybe you're in Maharashtra, someone in Australia, someone in UK. So everyone's location is different, right? Every country's location is different. Every city's location is different, and they exist on the sphere or on the surface of the sphere, and they're talking about the state called psi. This is the psi. Psi is the vector that based on the alpha and beta. Alpha is the probability, beta is the probability of 1, right? And it forms a sphere called Bloch sphere. And this is possible using this electronics called ion trap, topological qubit, photonic qubit, or superconducting qubit, right? So we are actually generating the third state apart from 0 and 1 in terms of our existing knowledge 0 and 1. We are having now 0, 1, and also the third state, the mixed state, right? It can be anywhere on the sphere. So this is also some very important property called quantum decoherence. The superposition of qubits causes like quantum decoherence. Superposition means when they superpose, they form this kind of structure called superposition. And there are various physics of superposition. I'm not going in detail of it. So if you want to develop a quantum circuit, we call it SDK, software development kit. IBM has QSkit, QHash, Google Crick, the different language. These are the Project Q, and so many SDKs are available. Okay. In our existing project, I told you that I have a project with Moha madam that is called machine learning for retinal image analysis and detection. So we are getting help directly from Amazon. Our project is sponsored by Amazon. Why sponsored? Because to access this quantum computer, you have to take the support of this kind of platform, and it's very costly affair. It's not possible for. It's not matter of 1,000 rupees or 10,000 rupees. It's several lakhs they charge us. So they are also developing the product. They are also charging for commercial purpose. For 1 qubit it may be free in some cases. Like IBM, it was free. Now they're also charging. Microsoft Azure also have quantum. Google also has a quantum AI, right? So I think today we'll be giving a presentation on Amazon Bracket after sometimes. Also, we'll be giving you the this IBM Q platform where we'll be telling how this quantum computer is actually working together, right? So when you're talking about quantum circuit, just like our normal logic circuits, AND gate, OR gate, NOT gate, multiplexer, demultiplexer, quantum circuits are also very important. And these quantum circuits are reversible in nature. Reversible means number of input is equals to number of output. And also, that reversible logic power requirement is less. Loss is less, right? So reversible is the most important property. I think in this FTP, ISG sir is giving full topic one day talk on reversible logic circuit. Okay. So lots of circuits are nowadays available for reversible system for quantum circuit generation, right? Reversible, I also do a lot of research in this field of reversible quantum computing or using quantum dot cellular automata and all these things, right? Reversible computing is one of the very interesting and challenging also to reduce the power requirement, right? So these are the existing logic gates for quantum computer. Just like our classical gate, we have Pauli X gate. This is the state X and Y set. Hadamard gate, this is the function, this is the matrix. Now, Generally, in case of uh, quantum computer, it's represented in terms of a matrix, right? 0010. For Hadamard gate, this is the matrix. For phase, this is the matrix. Shifting gate, control C naught gate, control not gate. These are the notations. And control Z gate, this is the notation. This is for swapping gate, swapping of two numbers, right? So this is the swap gate. So we can see the swapping. This is the matrix for that. Also, we have various kinds of logic gates. Started by Richard P. Feynman in 1986. It's very old technology, right? 1986. Feynman, at that time they developed those models. That quantum models. Various other circuits are also available. These are the basic logic gates, right? And ultimately, when you are doing this logic, you have to do the measurement. This is a measurement circuit is represented by this arrowhead, right? Measurement or observation of the result. What is the state? What is the condition of the state in the Bloch sphere that can be measured by the circuit? Okay. These are basics of quantum circuits. If you see the classical machine learning, what happened? We are giving an input. We have a machine learning model like deep learning or LSTM model or reinforcement model. There is some prediction rules are there. So we give a new example, case study. So retinal detection of some disease. So there is some prediction rules. Based on that, some result will come. Model predicts whether the number is odd or even, or the person has disease or not. Right? Means it's image analysis and something like that. So this is a basic workflow for conventional existing machine learning. But quantum machine learning, we have to use the quantum circuits, quantum prediction rules, quantum machine learning models. I will show you one by one how it is different. So in case of quantum computing and machine learning, it is combinedly called QML. That is the topic of today's lecture, right? QML, quantum machine learning, right? Quantum machine, QML. Now, if you see the quantum machine learning, what happens that something you are putting an image, any image, of a patient image. Now you are getting this, this amplitude encoding, and we are getting a Q bit out of it. See, it is 2 input, 2 output, so it is a reversible logic circuit. The 2 input, number of input is number of output. I think ISG sir will explain. It can be 3 input, 4 input, but number of input must be equal to the number of output, right? That is the basic logic of quantum circuits and quantum logic gates, right? So this is a qubit. From normal image, we are converting to qubit using this encoding process called amplitude encoding process. Where it go to the hardware? Hardware means from your circuit it goes to the hardware, quantum hardware. That using the classical computer means I told you in the beginning, from my own laptop through which I have joined this FTP. This classical computer connects the data to this quantum hardware. So you have to have the login. I think you have to purchase or you have to give the access to this IBM quantum computer or Google quantum computer. We are using Amazon. I think Mara will give you the example how we are accessing this Amazon bracket system. Using this classical quantum computer, we go for one iteration. Then we calculate the loss. A loss value goes to the classical computer. Again, the process will continue unless and until the loss is minimized. Now, this is a totally iterative process. So, full process is not quantum. So, it is a 50-50. Classical versus quantum means mixture. Classical to quantum, quantum to classical. So, that is another biggest challenge. So, accordingly, the hardware and software is developed. So, we are not now on QQ model. QQ means quantum model. Now we are using CQ model, classical to quantum model. CQ model, classical to quantum. Classical computer means on desktop or laptop, we can access to the IBM computer, then this loss function will continue. So this is the iteration will go and on and on. But one thing is that when you are accessing this quantum computer, processing is so fast, we can do it in fraction of second, the proper process. But problem is, these hardwares are not free. I think we have to wait for maybe 12 hours, maybe 6 hours, based on the busyness, that availability. We have to wait for this system to be operating in this zone, like this. So this is the basic working principle of this QML, quantum machine learning, right? So we are writing the script using Python or IBM or bracket as thing, and using that we are accessing this quantum computing. This process will continue and we'll get the result. The desired result. We are predicting something or hardware or not. Everything will get like this. Just a minute. Now this is the architecture of edge to quantum, edge to cloud. Thank you. So we can see that there is a edge computer to cloud. We are actually connecting through this domain. And this quantum cloud, nowadays we are accessing this quantum cloud and these edge devices like your laptop and also the fog device. Fog is your server in your college server or something like that. We are connecting this quantum cloud using this process, edge to cloud process, right? So cloud is here. So quantum cloud is here. So, but if you use the service, quantum as a service, you know that in terms of cloud, we are calling out what we say that what are the services in cloud? Platform as a service, software as a service, and infrastructure as a service. Platform as a service, software as a service, infrastructure as a service. Now, in case of quantum computer, we are having now quantum as a service, QS. So QS is now so popular, quantum as a service. So it is possible in this architecture, and this service is achieved, rather received by this edge devices, right? So edge devices, why edge device? Because if we give the service to the edge devices, it becomes much more faster. Why? Because we want the service at the doorstep only, right? Isn't it? In West Bengal government, there is a service. The government is coming to your doorstep. Duware kind of sense, door service. Similarly, the quantum service will get at the edge. So the laptop, mobile, everyone will be getting the service out of it. So this is actually the basic architecture of servicing architecture, right? If you see the quantum computing market is increasing like exponentially, especially the quantum machine learning. 2030, this is 24, 18 to 125. Huge amount of quantum jump we can see from 21 to 2030. Okay. So these are the requirements of quantum computing in terms of quantum to cloud. What is called quantum hardware, network connectivity, quantum software, security and scalability, and also interoperability. These are the various that requirements. Quantum hardware, network connectivity, software, security is very important. Scalability means what? In a Zoom, we have 10% can attend, 100% can attend. Scalability means we can increase and decrease the size based on the demand. Scalable, right? In our house, if you have a very good power backup, we can make 1,000 light on. It can be 10, it can be 100, it can be 1,000, it can be 10,000. Scalability means it can be increased and decreased like a elastic. We can do it, right? So scalability is a very important terminology in terms of quantum computing domain. And last part is interoperability. That means various heterogeneous devices. If you want to connect, interoperability is one of the very important property of IoT, where we can connect the heterogeneous devices together. So it is called unity in diversity, right? So interoperability is playing a major role so that the quantum services can be achieved. And the quantum machine learning services, whatever we are giving, achieved by everyone. Okay. So these are the 6 basic requirements for quantum computing in terms of cloud. And you'll be happy to know that many of the cloud service providers like Amazon, like Google, they're also using these services. And even believe it or not, you are using Gmail and all these services. They are now slowly migrating to this quantum domain so that they can give access to huge amount of users. That. So hardware requirement is very high. Also quantum connectivity, quantum software, quantum as a service software, APIs, SDKs, they're very important. Security is playing major role. Scalability I have already discussed, and so interoperability. So you have to keep in mind when you're talking about quantum machine learning or quantum computing, these are the very basic requirements. Right? So it is here given quantum hardware to connectivity, to security, to scalability, to interoperability. These are the requirements of quantum computing or quantum computing in the cloud domain. So quantum, actually we are getting quantum computing as in terms of cloud only, because we don't have quantum computing in my house, right? We are getting the quantum computing service as a cloud only. So we are mentioning multiple times quantum computing in cloud computing domain. So it's called quantum cloud. And simply we can tell you it's a quantum cloud. So why these are the requirements, basic requirements to explore. So QML is the not a buzzword. Already last 5-6 years we are last 5-6 years scientists are working in this domain of classical to quantum computer, and this classical we are getting the in terms of parametric input with logic gates, quantum computer to classical, then reversible logic gates, quantum gates, we are getting quantum. So classical to quantum, the domain is is moving on and on. So when today we'll show the demonstration how we'll connect this classical computer to the quantum computer and what kind of gates we'll be designing, and this whole process will be completed. So there are various kinds of learning steps, right? Machine learning steps, enhanced data processing, optimized resource allocation. These are the advantages of QML, quantum machine learning. Enhanced data processing means huge amount of data can be processed in a real-time manner. Real-time, mind it, like traffic control systems, satellite control systems. Optimized resource allocation, where we will be using which one. Resource allocation can be done very easily. Improved security and privacy. That using quantum key distribution, the satellite networks are operating, and they're using extensively this quantum machine learning and quantum key distribution techniques for secure communication. I am also editor of a journal called IET Quantum Communication. If you are interested, you can publish there. You can see the journals, the papers, all these things. Quantum Communication by IET, Institute of Engineering and Technology, and the headquarters is in London. So we have a journal, and recently this year this journal got impact factor of 2.5, and also ESCI journal. So those who are interested, they can go through it. We are also working various domains of privacy preserving techniques using federated learning, also advanced machine learning like quantum deep learning. So see, deep learning, everyone know we will be having the model called quantum deep learning. Reinforcement learning, we are having quantum reinforcement learning. So only we are using different quantum gates instead of normal logic gates. So that is the basic difference we are getting in terms of logic simulations, right? So also we have federated learning. Federated means where multiple, that distributed networks, multi-party network, we are getting quantum data together. I'll show you what is federated learning, how it works, and how the system can be utilized for various operations. Federated learning is one of my research area, and also I have a research project jointly with Madam Mohammed. She'll be. So I told you that quantum computing as a service, QCAS, we can see that quantum computing, this is the quantum computing, and the people, like I said, my name is Debashish, and I'm using this quantum computer, and she is a Mohammed Madam or something, anyone who is using the various drone operations, applications, see? And this is actually brain where this operation is happening. Nowadays, we are also having quantum neural network, quantum deep learning techniques, quantum spiking neural network like a brain that can be also achieved using this quantum computer, quantum circuits. Quantum computing as a service, QCAS, is one of the very popular uh, keywords, I can say, buzzword in terms of machine learning techniques, right? So when you're talking about machine learning, it's a hybrid classical quantum machine learning. As I said that it is a classical to quantum, so it is a hybrid. Quantum to classical is a jointly we are allocating the data together. Also, we have remote access to the quantum computers. Also, we have using quantum resilient cryptography. I think in this FTP, I think some of you will talk about quantum cryptography, BBQ, BBQ80. So many other circuits are available, used in extensively in defense domain. These quantum circuits. Also, AI and machine learning is playing major role in quantum domain. Lots of research is happening in this area. So if you see the platforms, I already have mentioned that IBM, Amazon. So I'll show you today. We will show you today these two things. Also, we have Regeti. These are all paid, mind it. These are not free. We cannot access it free of cost. As Microsoft Azure, they are also providing services. So we have the software called software plus hardware platform. See, I've written IBM providing this superconducting. Google is providing superconducting. Alibaba, they're also providing superconducting. Microsoft topological features. Intel uses spin quantum computers, spin qubit, spin. We call it spintronics. New area, not electronics, spintronics. So it takes the electron spin up and down. Accordingly, it processes the system together. Honeywell started IonQ, means ion-based quantum computer. Trapped ion D-Wave is one of the very popular quantum computers. Okay, IonQ use trapped ion computers. Zendu use photonic crystal. So these are the various kinds of hardware and software, and these are all developed. They're not so stable. They're developing more. So lot of research domain is available in this area. Okay. So this is the hardware plus software combination. Only software, if you see the simulation platform is called. I think Madam will show you the simulation also today after say 15-20 minutes. Qubit, 1 qubit, CQC, CQ wave, quant simulate, quantum circuits. Many of them are free of cost. Not all. Some of them are free of cost. Those who are interested, they can use it. Right? So these are the combined platform and hardware softwares are available in our hand. Okay. But there are some challenges called complexity. The complexity is very high because that is the reason quantum computer is not with us. So biggest challenge is that the temperature and the pressure problem. Scalability is another challenge. Security, interoperability, because of heterogeneity and cost. One quantum computer costs several billions of dollars. That is the reason in India we have only few quantum computers. That is also very low qubit, right? So system is not yet mature. That quantum technology, although we are discussing here, the system is not yet mature. It will take maybe another 5 to 10 years time to mature this technology. Maybe I cannot predict, but we hope that in future we'll be getting mature technology like this. And there are various, we develop certain software, and this is the quantum software engineering services. See, so quantum function as a service. So quantum software engineer, they're developing the services called QFAS using this quantum circuitries. QFAS API gateways, we are getting various kinds of code repositories, functional logic analysis. So this is for API, and also classical cloud layer is there. So there is a monitoring there. So this is a total functional platform for quantum software engineers. Okay, quantum software engineer. Mind it, we are all talking about software engineering, right? Now this is quantum software engineer. Very interesting area, and very evolving and emerging, and also very high-paid job. Those who are interested to become a quantum software engineer, they are very good prospect. So a lot of people are working on it. This is one of our published paper in FGCS. Professor Rajkumar Bhuiya, my student Annesha Mukherjee, they developed this model. Quantum function as a service for monitoring these functions, quantum functions, hybrid functions, quantum simulator, everything. So this is actually the platform, how we using this, that we are getting the cloud services to the quantum computer. So Already I've mentioned that complexity, scalability, security, interoperability, cost, and maturity. These are the challenges, okay, for this quantum as a service. Some company called Terra, they have developed this model. See, quantum as a service model. They've already coming into the picture. They're giving quantum vendor. Quantum vendor means they will acquire the hardware, processor, memory, simulators, and accordingly they will give you the user. Say, I am the user. So I want to use or simulate, compute, or store. Just like your Gmail, we can store it. Just like your Facebook account or social account, we can store the data, like our Gmail in quantum computer. Or we can also compute, means we can do calculation. Or we can use simulator, right? I think Madam will show you today this two, right, Madam? Simulator and the computation, right?
Yes, sir.
Okay. So we will not show you storage, but storing is also possible. Okay. So we are more interested now in simulation and also to compute. Thank you. So this is the user platform and this is the quantum vendor. Vendor means the service provider. QCAS, see QCAS. Request will go, provider will provide service, and developer will see this module. This is actually the ecosystem of quantum computing or quantum machine learning, right? So that we can provide these microservices. And these microservices are developed by the quantum software engineer. And this is a very important and very interesting slide in the domain of quantum machine learning and quantum computing, right? So that we can get various applications like bio-inspired computing, quantum optimization, quantum cryptography. All these things will happen together. They will work together, right? So, see, I already mentioned this quantum entanglement. So I told you that already I'm using this IBM Cube quantum computer. So today will be demonstrating on it. There are lots of applications in healthcare, drug delivery systems, that also in mining, machine learning techniques, also in healthcare. So many applications are there. Already many papers are published in COVID-19 also. Quantum computing plays a major role for discovery of drugs and finding out the disease in the lungs disease and everything. This is the quantum circuit, equivalent quantum circuit for this cognitive machine learning systems, right? And these are the corresponding hybrid. See, all are mostly hybrid classical quantum computers. So nothing is pure, basically combined with classical and computer domain. Also, in neural network computing, it published classical quantum computing, right? Segmentation and so many things. Since I told you already, Hadamard gate, Toffoli gate, GHZ gates, so many. These are the logic gates. These are the components. So first you have to build, then you have to test, then you have to run, and then analysis. So today we'll show you using Amazon bracket how we'll build, test, run, and analyze these quantum computers, right? See, these are some of the rates, means cost, pricing for quantum simulators. This is for East Virginia, and means you can change it based on the availability, based on when you log into the Amazon bracket, they will provide the services. Based on the pocket, means how much amount you want to spend, accordingly you can spend it, right, from this service providers. So this is the quantum services we are getting. I think Madam will demonstrate in detail all these quantum circuits and quantum hardwares. See, this is the roles for how we can complete the services and various levels. March 24, December 2023. So these are the logs of quantum computing. See, these are pricing. It's not so easy to access. It's very costly. The circuits are very costly. If you do not have any project, it's very difficult to handle, right? So this is the project. I think Madam will explain it. Amazon, our project title is Federated Quantum Learning Neural Network for Privacy Preserving Classification of Retinal Images. We worked on retinal image. So this is a retinal image. I think Madam will explain in detail how this retinal image we analyzed using these quantum circuits called QNN, Quantum Neural Network. using these qubits. So actually, if you see this domain of quantum machine learning, we are actually combining three areas: AI means machine learning, IoT, and big data. So quantum computers are capable enough to handle the big data in the IoT domain using this artificial intelligence, right? So we used federated learning. Federated learning is also known as distributed learning that provides privacy, performance, and scalability. So distributed learning means actually, if you see multiple mobile user, they send the data to the global level. The aggregation is happening at the global level, but local level learning is happening. So this is known as local learning, and we are aggregating all the data to the server at the top. We call it global aggregation. Okay. So by this process, we can get high level of protection, efficient user resource management, modeling. Training time will be real time and also personalized. No identity will be disclosed, right? So this is a federated learning technique where we can see there are, say, 10 lakh customers are there. Out of that, we have chosen 100 customers, 100 users. From that, we developed a model using this help of quantum engineers. So quantum engineer may have developed 10 best models. Out of the 10 best model, the best model, see deep red color, violet color, that will be deployed to all the quantum computers like this. So by this way, actually deployment processing is happening. Deployment is happening, right? Using this quantum engineering process, right? Okay. So this is known as federated learning. Federated learning means we are aggregating data in the server, but we are getting the data from the local level, but the identity of the user is not disclosed. Why? Because training is done here, but no one's identity is disclosed. So federated learning is also providing privacy preserving. So if you have multiple drones can also send the data. So W1 is the weightage, W2 from drone 2, W3 data will get from drone 3, WN data will go for this fourth drone, and ultimately W1, W2, W3. See, the arrow is from the drone to the server. We are doing a summation, Wi 1 to n, means from n number of data we are gathering it. From the data we are making a pattern using quantum machine learning, and after quantum machine learning, the global pattern is WG. W1, W2, it becomes a global pattern, WG. And see, if you see the lines carefully, this is the forward line, and WG line is going to the backward. So the global pattern will be distributed to all machine learning tech, means all the drones. So global, it is similar to our WhatsApp update. Sometimes we update the WhatsApp, that is called WG, global pattern, right? So by this way, we can process the system very efficiently in a distributed fashion using machine learning techniques, right? So this is also known as quantum machine learning, okay? Quantum computing based machine learning. Also, see, if you have thousands of drones around India, quantum computers can do it very easily. You know that our Prime Minister is now in US. He's talking about drones, and so many drones will be giving border security. So only quantum computer is the solution. Quantum-based SDN, software-defined network, is the solution to provide the services at the doorstep from various corners of the world. So drone service is now quantum drone, QD, quantum drone, right? So if you see the logic circuits of federated learning, see these are the circuits where we are getting the user data aggregation, and ultimately summation, all the data is going to summation data is going to the user level. The total cyclic process. This is also total cyclic process. See? One data is going to here and coming back. Similarly, here also data is going back from here and coming back to this. So this is a global pattern is distributed. Federated learning, this is the circuit of quantum machine learning techniques. So these are the circuits, the data, input data. This is the encoding data. These are the logic gates, and this is the measurements. See, I told you this is the measurement gates, and all the data is after prediction is updated like this. This process will continue unless and until we get a desired result. So there are three steps of machine learning, quantum machine learning. First is a input data in terms of bracket, with these things we call encoding. Second is gates for optimized parameter. Third is a measurement, and the process will continue the prediction, update the loss. The process will continue unless and until we get the result, right? This is for say any kinds of image analysis, This for also deep quantum neural network. Same thing. Preparing of data, quantum evaluation models, sample averaging, and evaluating the classical models using quantum wave function, right? So there are so many circuits are there. So this is another disease detection. So many circuits are there. So classical layer data will be fed to this quantum computers. This is the measurements. Quantum device will detect fully connected or partially connected, whatever. The feature will detect whether disease is there. They tick green tick, or if it's not no disease, then red. So by this way, actually, we can detect the disease is there or not. Okay? Yes or no. So it is very fast and very efficient and very, the efficiency is very high. That is the reason we are migrating from normal classical machine learning to quantum machine learning, right? So many other image analysis is there. Okay. Thank you for your patience, Harry. Any question I can take one or two. Yes. So, anyone is there? Is it understandable or not? I cannot.
Yes, sir.
Okay. You got some idea, madam? Priyadarshini, madam? Yeah, you got some idea?
Yes, sir. It's a really interesting session, sir.
Okay. Now, we have Mohan Ondipal, madam. She will practically demonstrate slowly, next 1 hour, how we are implementing this using this quantum computer. She will live login in front of you from the classical means our laptops. We will log into our quantum computer, right, madam? We'll go to INQ and IBM, right?
Yes, sir.
So she will demonstrate. It takes time. So you have your patience, and we'll give you live image analysis, and we have published some work also in our project. So I want to show you there. Okay, over to madam. Thank you.
Thank you, Professor Debashish there. Am I audible properly?
Yes, yes.
Yes,
Okay.
ma'am. Yes.
Okay. Thank you, Professor Debashish there, and thank you, the organizers also, for giving me the opportunity to present our work. So I will try to present our work so that everybody can understand how the quantum machine learning models are created, how the models get trained, and how the evaluation takes place. I'll be trying to show all of you properly. So I'm presenting my PPT. So I think my screen is visible right now. My screen is visible.
Yes, ma'am.
Okay. So I'll be trying to discuss about the execution and application of different types of quantum machine learning models. And particularly, I'll be explaining different QML applications in the medical domain or in the healthcare domain. Because we have a project in the healthcare domain, quantum machine learning project.